All right, here we are in Chapter 6, Section 4. We're looking at some exponential growth and exponential decay. So our essential question is, what are some of the characteristics of exponential growth and exponential decay functions? So now we're going to check out our learning targets. So this is what's going to focus our thinking and our work today. So we want to use and identify exponential growth and decay functions. Our second one is we're going to interpret and rewrite exponential growth and decay functions. And then thirdly, we're going to solve real-life problems involving exponential growth and decay. So the first thing we want to actually look at is, what is an exponential growth function? So exponential growth, remember, we kind of talked about this in the last section, is where something increases, right? And we're talking growth, so it's going to be an increase by the same factor. That means, remember, we're multiplying by the same thing each time. So here's my function, y equals a times the quantity 1 plus r to the t. So a has to be greater than 0, and r also has to be greater than 0. And if both of those things are met, we're talking about an exponential growth function. So this y value is our final amount, right? If we're talking exponential growth, we can always think of population, right? So our final amount would be like, what's the new current population? A is where I start. That's my initial amount, is where I start. This entire thing that's inside my parentheses is considered my growth factor. And I'll know it's a growth factor rather than a decay factor, which we're going to talk about in just a minute, is because this is going to always be greater than 1, right? Because I'm adding 1 plus something else, so I know that this is going to be greater than 1, so it's a growth factor. So this r value is my rate of growth. This is always going to be in decimal form. So often we're given rates in percentages, so we have to first convert it to a decimal to put it in here, and then I can add it. And then t, don't forget my exponent out here. T is always time. And in the problem, you will be given what time frame you're looking at. If you're looking at minutes or years or months, those kinds of things. So now let's look at an example. Right, here's example number 1. So the inaugural attendance of an annual music festival is 150,000 people. The attendance y, so attendance is y, right, increases by 8% each year. So we have to write an exponential growth function that represents the attendance after t years. And then we're supposed to figure out how many people will attend the festival in the 5th year. So let's look at the things that we have. Okay, so I'm starting with an initial amount. Remember, I start here. I have a growth rate, which is, again, given in percentage. And I always want to change my percent to a decimal first. And in order to do that, I take my percent sign and I move it to the left 2 places, and that becomes my decimal. So here there wasn't a second place, so I have to put a 0 there. So here is my decimal form of my percentage. So now I have all of the information that I'm going to need. Okay, so now I can write my exponential growth function. So remember, here's our parent function. And here's the things that I know. I knew that 150,000 was my initial amount, and my growth rate was 0.08. So now I can kind of simplify, right, because I can add 1 plus 0.08 to simplify in here, and I have my function written. And that was the first part. That was part A. So there's my final answer. So then in part B, I was asked to find the 5th year. So here's the thing that we have to keep in mind. We're going to use t equal 4, because when t equals 0, that's the first year. Because remember, anything to the 0 power is 1, and so that would give us our initial amount in the first year. So we're talking 4 more years. That's what this t equals 4. So I have my function that I found above, and all I do is substitute 4 in for t, and then I go ahead and I simplify that. And so when I'm simplifying something like this, I always want to do the exponent first, right? And so here's just the calculator that comes with your computer, which you can use always, right? And so here's the button that I'm going to use often. So I have my 1.08 to the 4th power, which gives me that long decimal, and then I'm going to multiply that by 150,000, which gives me my final approximation, right? And you'll see that that's approximately what we get here as well. It's 204,073. Now here, you see I don't have any decimals after this, even though I figured that out in my calculator. And the reasoning behind that is because this y value was population. So we're talking about people or things, and we can't have a fraction or a decimal of people. So then we just rounded. Approximately 204,000 people will attend the festival in the 5th year, right? Again, we could leave it as this number, but we don't ever want to put that decimal when we're talking population because it's not a realistic thing to think about. So here we have one of your monitoring progress. Go through and see if you can kind of follow along with what we did on the first example and do this one. So now here we're looking at growth exponential decay functions, okay? If you'll see, this looks very similar to what we just looked at. The only difference is if it's growth, there's a plus there, and since this is a decay, there's a minus. So here's the same thing, right? A has to be greater than 0. R here, right? R had to be greater than 1 in our last one, or greater than 0. So here, R has to be between 0 and 1. Okay. So again, Y is my final amount. The A is my initial amount. Here's my decay factor, and it's a decay factor instead of growth because it's subtraction. And we'll see that this is always going to end up being less than 1. So, right? So this R is my rate of decay in decimal. Again, we're going to often be given in percentage, so we first get it to decimal, and then T is my time. So now let's look at an example here. So this in your book is example 2. So we're going to determine if we're looking at exponential growth or an exponential decay or neither. Okay, so first I have to kind of see what's happening in all of my numbers. So for this part A, I see that each time my x goes up 1, I multiply my y times 1/3, right? Or I divide it by 3. So you'll see how this is going down by the same amount each time, by the same factor. I'm multiplying by the same thing. So I know that this is going to be exponential decay. And I know this because this number right here in red is less than 1, and I'm multiplying by the same thing. So let's look at B. So I see every time my x goes up 1, I multiply my y by the same thing. And I multiply by this value that's greater than 1, so I know that this represents exponential growth. Okay? So here's another monitoring progress. So take a look through this and see if you can figure out if it's growth or decay and why that is. So now we're going to be looking at example 3. So I have to determine whether each function is growth or decay. So in the last one we looked at a table of values, and now we are looking at some equations. So let's look at part A first. So I see I have an A value, right? And here's my whether it's going to be growth or decay right here, and my exponent. So I have to write it in the right form. So I use my growth factor to find the rate of growth, because I'm also asked to identify the percent rate of change, right? And I see that this in my parentheses is greater than 1, so I know it's going to be growth, right? Because it's going to be 1 plus something. So I can write out my equation, whatever's in my parentheses. 1 plus r equals 1.07. So I know that r equals 0.07, and here's in decimal form, so I want to get it into percent form. So again, I take my decimal and I move it 2 places to the right, and I draw my percent sign. So that becomes 7%. Okay, so let's look at B. So I have my A value. I see that inside my parentheses is less than 1, so I know that it's going to be my exponential decay. So now I just have to figure out the percent decay. So again, I take my decay factor, whatever's inside my parentheses, and set it equal to what I see. Then I solve for my r, and I see it's 0.02. So again, to find my percent from that decimal, I take my decimal and I move it to the right 2 places and make my percent sign. So my exponential decay, my rate of decay, is 2% on this one. Okay. Here we go. This is example number 4. So I'm supposed to rewrite each function to determine whether it represents growth or decay. So first I want to just write the equation that I'm given, and then I can simplify it, right? So you'll see the different thing here is I don't have just t up in my exponent. And in order for me to have growth or decay functions, I have to have just t as my exponent. So I have to kind of solve and simplify for that. But knowing the properties of exponents, which we've worked on in this chapter, I can rewrite this function and help me solve. So I know that t divided by 4 is the same thing as 1/4 times t, and so I can use the power of a power property to undo that kind of. And then I can evaluate this power. And by doing this, I just put it in my calculator, right? 0.96 to the 1/4 gives me approximately 0.99. But now my exponent is just a t, which is what I wanted. So I see that this part inside my parentheses is less than 1, so I have a decay function. So let's go ahead and look at b. Okay, so I'm going to just write my function how I was given, but I see that I have more things in my exponent than just my t, just my variable. So I have to get rid of that first. Well, and I know that when I'm subtracting exponents, that's going to be my quotient powers, my quotient of powers property, right? So I can rewrite it as this, and then I see that in the denominator is something that I can actually deal with. So I can evaluate this, and then I end up with just my exponent, and I see that inside my parentheses is greater than 1, so it's exponential growth. So I always have to, before I can determine if it's growth or decay, I have to get the exponent to be just the variable that I'm looking at, which in most cases is the letter t. So here's some more practice, monitoring progress. Go ahead and do these and see how you're doing on these problems. So now we're going to be looking at solving real-life problems. Remember that third learning target today is using this information with real-life problems. So often we talk about compound interest. Okay, so compound interest is money that you earn on money that you have in the bank. So if we have compound interest, that means you get money on the principal and on the interest you've already earned. So here's the equation that we're going to use for our compound interest, right? Y, again, is going to be what we have now, right? Our ending amount. P is my principal amount, what I'm starting with. The R is my annual interest rate, which is going to be in decimal form. Remember, I want everything in decimal form. T, again, is in years. And N is going to be the number of times the interest is compounded per year. So if you see a problem that says having compound interest compounded quarterly, I have to think of how many quarters there are in a year, and that will be n. So I know that quarterly means 4, so my n value would be 4 in that example. So let's look at an actual example and work through it in here. So this, if you're following in your book, is example number 5. So I deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after t years. So first I want to see the things that I have. I see that I have an initial amount. I have my percentage, and I don't like percentages when I'm dealing with numbers, so I want to go ahead and make this into a decimal. So I move it over twice, so it's 0.06. My interest is compounded monthly. Well, I know that monthly means there are 12 months in a year. So then I'm going to write my function. So now I have all of the information that I have. So I take my parent function, right, my original function, and I plug in the things that I know. I started with 100, my 0.06 interest, my n, right, was 12 because there are 12 months in a year, and then I have my t. So that will tell me if I want to say, well, in 7 years, how much money will I have? Well, now I can just put in a 7 for t and go from there. So then all we did was we simplified. Using our calculator, we have 0.06 divided by 12 plus 1 gives me this 1.005. And I know that I'm on the right track because interest, when I earn interest, my money should be going up, so it should be growth, and this is greater than 1, so I know I'm looking at a growth equation. Okay, so this here is example number 6 in your book. So the table shows the balance of a money market account over time, right? Money market is just a fancy type of account that you can have at a bank. So I have to write a function that represents the balance after t years, and then graph the functions and compare, right? So I'm going to graph the function from the last example we did and this function and compare my balances. So the first thing I have to do is I have to figure out all of my pieces, right? And I know my initial balance is $100 because I'm told that at year 0, right when I very start, I have $100. And I figure out that it increases 10% every time. And I can do that because I can use my calculator and I'm going to take my 100, my new, so my 110 divided by 100 equals 1.1. So this tells me how much it went up. So let's see if it works again. So I've got my 121 divided by 110. 0.1. So I know that that is going to be my percent, my R value. Right? So that's where they get this R value from, is by dividing the numbers in order. So now I can write my formula, right, with my initial amount, with my R value that I just found, and I have my T. So I substitute what I know, and then I simplify. So now I'm going to graph my solutions. So I can go ahead and use a graphing software. So I'll go ahead and use Desmos or a graphing calculator in order to do this. So you'll see that in my last example, right, in example 5, this was my function that I came up with, and for this example here it is. And I graphed them, and I started with the same amount of money in each, and I can graph them and see what they end up with. So now I can see that I'd rather have the blue one. I'd rather have this money market account than the previous account. And I can see that also in words, because this, my R value, right, to turn this into a percent, I go ahead and I move my decimal over 2 places. So this would be 10%. And I know that 10% interest is greater than the 6% that I was told in my last example, so I know that I'd make more money. But so now I can compare these using a table, I've compared them using the equation, and I've also compared the graphs of them. So here's a monitoring progress, so go ahead and try this one, see what you come up with before we move on. So here's kind of our last example that we're going to look at. This is example number 7. So the value of a car is $21,500. It loses 12% of its value every year. So first I have to write a function that represents the value after t years. And then I want to find the percent decrease, and then I want to graph it to estimate the value of my car after 6 years. So let's look at what we have. I have an initial value, right? That's what it was when I got it. 12%. I don't like percents, remember, when I'm dealing with this, so I want to move my percent sign and make it a decimal, so it's going to be 0.12. That's all of the information that I need in order to write my equation. So I know also that this is going to be a decrease, right? It loses 12%. So I know that this is going to be decay. So I can keep that in mind, that this is decay. Whoop, wrong button. And I know it's decay because it loses value. If it was to gain value, that would be a growth function. Okay? So I'm making my plan, and I'm solving the problem. So first I have to come up with all the information that I have, right? And this is what we talked about. Here's my initial value and my rate of decay. So then I take my formula, and remember I have to figure out if it's growth or decay first, and I knew it was decay, so I'm going to be subtracting R, and I plug in what I know. My initial value is here, my rate is here, and then I can simplify and subtract, and so then I write my final equation. So then part B was I was supposed to find the percent every year. So I want to use the fact that time, right, is going to be 1 divided by 12. So because I'm looking for monthly, and I know that this was given to me in years. Okay, so I can use the properties of exponents and rewrite my function. So then I use my original function, and I plug in all of the information that I have to rewrite my exponents. I use my power of a power property, right? And I can evaluate the power and figure it out. And so my rate of decay is right there for you. Okay. So then I can always take my decimal, move it over 2 places, and turn it into a percent. So this is my monthly percent decrease. So let me step back here for a second to see what we really did. So I know that I have t as my exponent. Well, I want to look at monthly things, right? Not yearly, but monthly. So I know that I have to cut this into 12 pieces. But I can't just do that magically because that's not mathematically correct. So in order to divide it by 12, I also have to multiply it by 12. All right, so here I'm dividing by 12, here I'm multiplying by 12. So mathematically, I haven't done anything. So then I can use my power of power property to put this part in with this one, right, and to come up with my decay factor. So now I can look at the graph, and again use Desmos to graph your function, and we'll see what it looks like. So then approximately in 6 years, so when t equals 6, my car will be worth approximately $10,000. We can also figure this out using our equation. If we put 6 in as t, we'll still get the same answer as we look at from the graph. So this is just double checking. So here's when they say when you evaluate our function for t equals 6, we get approximately $9,985. So $10,000 is a pretty close estimation, right? So in my graph I got 10,000. If I use my equation and 6 for t, I end up with pretty close to the same thing. So you really just have one more monitoring progress to go through and check to see how well you're doing, to see if you're ready to move on. So let's review our learning targets real fast. Can you use and identify exponential growth and decay functions? And some of this is determining, is it growth or is it decay, and how do you know? Then our second learning target was interpret and rewrite exponential growth and decay functions. And we've done that in several places. Right, we have to figure out the growth rate or the decay rate, how much time, those kinds of things. That falls into this learning target. And then solving real-life problems involving exponential growth and decay. We looked at interest in a bank account, so we looked at some money that you're gaining, so that's a growth. And we looked at cars, and cars are a decay. So we've looked at both kinds of examples. So now go ahead and start working on your homework.